All right, well, welcome. The 4-day fMRI experimental design workshop. This is going on the seventh year that I've taught this thing. So there have been a lot of changes over the course of the last 7 years. When this first started out, it was sort of 4 people sitting in Mark Desposito's lab, and we just kind of went over a few issues in experimental design. And there, at that time, we were able to encompass everything that was relevant to the design and conduct of fMRI experiments in about 2 or 3 hours. And do it pretty completely with kind of time left over for questions and donuts and random conversation. But over the years, the field has grown so much that even with the 8 hours that we have blocked out over the course of the next 4 days, there's really no way that we're going to be able to cover every single topic in sufficient detail that we can say that we've exhausted the field. Nonetheless, the goal here is to try and give an overview of the basics of fMRI experimental design and analysis, the topics that you really should have some rudimentary understanding in order to be able to put together your own fMRI experiment. So even though the course has become bigger and there's a lot more people here and we're going to try and cover an awful lot of material, I'd like to try and keep this thing running pretty close to how it's been running for the last few years, which is a very interactive session. Now, even though we're in a new venue with sort of auditorium seating, I still want you guys to kind of feel like we're sitting around a table and have the opportunity to interrupt and discuss, right? So as you can see, it's just me, the whiteboard, and some colored markers. This could be a really tedious 4 days if you guys don't get into the audience participation thing a little bit. So please feel free to interrupt me, ask questions. If there's stuff that doesn't make sense, there's probably not a better opportunity to try and figure stuff out than in this audience. And with us sitting down to try and work out these details. So if you have a question, something doesn't make sense, put your hand up. It's almost certainly the case that a number of other people in the audience aren't sure about that topic either. So it'd be absolutely fine to interrupt me. There's no concern about that. I've built in a lot of extra time in the schedule too, so that we can kind of parlay and go over stuff without fear of missing our schedule. So that's the first thing. Please interrupt me. The second thing is, let's get a sense of the level of experience of the audience here. So who here has conducted an fMRI experiment and tried to analyze the data that's come out of it? Okay. And who here has never sort of worked with fMRI data before, and this is going to be like a brand new introduction to the field? Okay, fair enough. Okay, good. So we're gonna try and cover the entire range of experience as we go along here. And we'll be starting off with pretty basic concepts and then building them up to more complicated things. I should tell you that as we go along, we're going to come across a couple of mathematical, statistical concepts, which might at first seem a little daunting, but my goal here really is to provide you not with a mathematical understanding of a lot of these things, but instead an intuition, so a way to understand roughly kind of how things fit together and operate, even if you can't write down the equation that's going to relate one thing to another. Okay? I think there's only one equation that I'll put up on the board during the entire period of time, and again, we'll take that one real slow so we don't lose anybody. Okay? So let's take a look at the outline, and we'll kind of get a sense of where we're going to be going in the next few days. So on day 1 here, my goal was to try and lay down some of the basic language and techniques that we're going to use to build upon the following 3 days. So we're going to talk a little bit about where fMRI data come from. This is going to be fairly brief, but we'll talk just very briefly about the physics and the physiology that underlies bold fMRI data and similar sorts of neuroimaging signals. And then we're going to talk a little bit about inference. And so these first few comments actually are going to have a rather broad application to neuroimaging experiments in general and not even be specific to bold fMRI. We're just going to talk a little bit about what are the kinds of things you think you could learn by using a neuroimaging experiment. What's the kind of stuff you can learn about the relationship between brain and behavior? Okay, and then we're going to get really into the nitty-gritty. So there's a couple of core kind of intellectual concepts that we're going to need to get under our belts by the end of today. That's linear systems. We're going to have to understand what a linear system is, what a system is, and what the properties of a linear system is. And we're going to have to talk a little bit about the general linear model, which is the sort of centerpiece of analysis of bold fMRI data. In fact, not only bold fMRI data, but most parametric statistical analyses that you run across. So we're going to spend a little bit of time trying to understand exactly what those things are and how they apply to bold fMRI experiments. And then we're going to talk a little bit about the bold fMRI hemodynamic response function, which also is going to play a pretty fundamental role in guiding how we design experiments and talk about their analysis. So the subsequent days, you can take a look. I won't spend too much time now previewing them, but the main things that we're going to go over as time goes on are some of the properties of fMRI data in time. So temporal autocorrelation, this pink noise or 1 over f noise that you've probably heard about. We're going to talk about how to design covariates for use in these sorts of experiments, and then we're really going to get into how you design or arrange events in time to really optimize the power of your experiment to detect stuff that you want to see. But this is all the road ahead, and we'll hit that as we go. Okay, so Margaret, can you do me a big favor and grab me like a glass of water or something like that? I get dry as I ramble on. Okay, good. So let's start off right at the top with the basics of fMRI data, or bold fMRI data. So actually, and here's an appropriate point for me to throw in a quick caveat. I am neither a physicist, nor an engineer, nor a mathematician, nor a statistician. I am sort of a jack of a number of these trades, but certainly not a master of any of them. So if anybody in the audience has a background in physics, engineering, statistics, or mathematics, you're certainly going to come across points over the course of the next 4 days where I'm going to say something which is either slightly or grossly inaccurate, or is a gross oversimplification of something you know to be true. So I have no problem, and please do sort of put your hand up and say, like, oh, Jeff, are you leaving out X, Y, and Z? And that's fine, so we can have that as a clarification. But again, sort of the point of much of this is trying to give you the overview, even if we skip over some of the specific details as we go along. Okay, so since we're talking about fMRI data, we should talk about what fMRI data look like and where they come from. So just really the most fundamental place to begin is that bold fMRI data are volumetric time series data, okay? 4-dimensional data. And so what that means is that over the course of an imaging experiment, you acquire these volumes of data within which is contained the brain, okay? And you acquire these repeatedly over time, okay, where time is on this axis, okay? So it's just a simple 3-dimensional picture, volume of the brain acquired over time, right? And so each of these pictures is made up of tiny picture elements. If you get in really close to your TV screen, you'll see the individual dots that Seurat style make up the picture that you see on the TV screen. And each of those little dots is called a pixel. Well, in this case, since we're dealing with a 3-dimensional volume of dots that's making up this volume, these are called voxels, right? Voxels, vo for volume. And so each one of these little voxels then add together in this entire image to create this volumetric picture of the brain. So just to give you some numbers to kind of carry around for how many of these voxels there are and how big they are. So of course, this can vary tremendously depending upon the nature of the experiment you're doing and how you choose to run the scanner. But just as a broad simplification of the types of experiments that are most common around here, typically these voxels are about 3 millimeters on a side. Okay, and the total number of them that it takes to cover the entire brain volume is on the order of 16 to 30,000 voxels, depending upon precisely how big they are and how much of the brain you wish to cover in your imaging experiment. Okay, so an awful lot of little voxels that go up to making this picture of the brain. And then we acquire one of these pictures over a period of time, and it turns out that, oh, thanks very much. Oh, great. Turns out that the time between one picture and the next can vary. But again, typically for our sorts of experiments, it's on the order of, say, 1 to 3 seconds. Okay, so each picture of the brain is acquired either, say, every second or every 2 seconds or every 3 seconds. In fact, right now on our 3T scanner, the most common repetition time, or TR, that's what is used to refer to the time between one image and the next, is about 3 seconds. And we might have a chance to talk about later on why that 3 seconds turns out to be an optimal kind of spacing for the sorts of experiments we're doing. But we can take it as a given right now that we're going to get a complete picture of the brain composed of these tiny little volume elements about every 3 seconds. Okay? As we go along, we'll talk about what are the events that's really going on as this volume picture of the brain is being acquired, because it turns out we don't acquire the whole darn picture just as one flash simultaneous acquisition. We actually acquire slice by slice and row by row within there. And so that has some consequences for analysis as we go along later on. But for now, you can just take it as that we have these volumes of the brain, one acquired about every 3 seconds. So the first thing you should realize then is that the amount of data that we collect is tremendous. This can add up to a gig of data very quickly if you're acquiring these images, which have 30,000 voxels, one voxel one image every 3 seconds, and then you scan for a couple of hours, you're going to end up with an awful lot of data, typically about a gigabyte. Okay, so what exactly are these pictures? Where do they come from, and what are they related to? Okay, so as you guys know, MRI is based upon having a very strong magnetic field to start with. And so here is one of those occasions where physicists in the audience might clutch their chests at my dramatic oversimplification, but just to make sure that we're all on the same playing field for roughly where this stuff comes from. So the basic idea is that an MRI scanner is a very strong magnetic field, and that magnetic field typically has a particular alignment, which is referred to as the B0 alignment of the magnetic field. It further turns out that protons, which are contained on lots of different sorts of elements, but including significantly water molecules, so the protons in water molecules, act as little bar magnets. So they tend to have a particular polarity with a positive end and a minus end. Okay? And we won't get into the quantum mechanics of why this is the case, but so anyway, protons tend to have a plus end and a minus end. And so it tends to be the case then that if you take a sample of something, a jug of water, a watermelon or a person, and put them inside this very strong magnetic field, the protons, which are located within these water molecules, will tend to align themselves with that strong magnetic field, right? Each one's a little bar magnet. You bring two magnets kind of close to one another, they're going to tend to want to line up. Now, it's not the case, of course, that every proton lines up perfectly with the magnetic field. Instead, there's just sort of a population net alignment. Okay? So if you kind of sum up with the directions that all these different little protons are pointing, they tend to be pointing in the direction of the strong magnetic field that they're contained within. Okay? And as we know, we are made up of lots of water, and so the protons which are contained within the water molecules in the tissues of our brain, for example, will tend to align with the strong magnetic field. Okay. So a further property of these protons is that they spin or precess with a certain frequency. Okay? And that frequency of spinning is defined by the strength of the magnetic field that they're contained within. Okay? The strength of the magnetic field that those protons see. So, and that particular frequency is going to vary for different scanners, but has a particular frequency for our 3T scanner when you take some protons and put them within there. And it's further a property that if you then introduce radio frequency energy, the same kind of radio frequency energy that's put out by, like, when Channel 3 broadcasts its television signal, okay? So when you put out radio frequency energy like that, if it's at the precise frequency with which these protons are precessing or spinning, then the protons will absorb that energy, okay, and move from this low energy state of being aligned with the magnetic field to a higher energy state of being not aligned with the magnetic field, okay? So there is such a thing as what's called a 90-degree pulse, which is a pulse of radio frequency energy delivered at just the right frequency to match up with the precession speed of these protons, which takes the alignment of these protons with the magnetic field and shifts them out of alignment, okay, into this high energy state. Okay? So, but then you turn the radio frequency energy off, and these protons naturally are going to try and go back to their low energy state and relax back down to alignment with the strong magnetic field. Okay? And as they do so, they're going to give radio frequency energy back off. Okay? So in essence, the MRI scanner is basically a very strong magnet, right, with a radio frequency antenna for delivering energy and a receiver for listening to the sound of the protons relaxing back to their low energy state. Okay? It is the speed with which this relaxation kind of comes back that is the source of the primary form of contrast that we see in most of our anatomical MRI images, and that's T1 contrast. T1 refers to the time constant, or the exponential rate of decay of the time it takes for these protons to kind of relax back down to their alignment with the magnetic field. Okay? You know what? That's all I'm going to say about T1 contrast. There's a lot of really excellent resources out there for folks who want to learn more about MRI physics, including a book called MRI Physics for Dummies, which is very good, as well as there's a couple of websites which have very nice JavaScript graphics of protons precessing and spinning around. And I can give you guys those references. In fact, in the syllabus, I think I make reference to a couple of these different sources. Okay, so that's T1 contrast. So now we've already talked about how this alignment of the protons is sort of a population alignment. Okay, it's sort of the virtual alignment of all these protons, all roughly pointing in the same direction. Okay. Well, it turns out that there's kind of two ways that these protons can relax back to this low energy state. Okay, or that the energy that they give back when they're doing that relaxation can drop off. One way that energy can drop off is by this main direction, this main vector of alignment coming back down to being in the lower energy state. But it turns out the other way that this can happen is if the protons fall out of phase with one another, if they don't spin together at the exact same speed anymore. So what do I mean by that? Well, So what you can think of is that when these protons receive their 90-degree pulse and sort of move into this higher energy state, all of them are spinning at exactly the same frequency, okay, and with exactly the same phase. So you can think that the alignment of all the protons is perfect. Here's proton 1 and proton 2 and proton 3 and proton 4, and they're all sort of spinning and rotating at exactly the same, in concert with one another, okay? Well, what if it was the case for one reason or another, and we'll get into the reasons, that the protons start to spin at just very slightly different rates, like this one spun just a little bit slower and this one spun a little bit faster, and so over time they start to diverge from one another, okay? Well, this signal would also decrease because it's the case that you would be losing kind of your population, right? So you can imagine if you have a whole crowd of people and they all say, 1, 2, 3, yeah, and everyone yells yeah at the same time, you'll get a big, strong, coherent yeah coming out of the population. But if everyone kind of counts on their own silently, 1, 2, 3, and happens to say yeah at a different time, then you're not going to get that strong sort of population, woo, go Eagles. Instead, you'll get some sort of like smattering of quiet that you hear, in Pittsburgh when there's cheering, right? So you'll have sort of a discordancy of all the different components of that population not firing at the same time. Well, this is the same kind of thing. If those protons get out of procession with one another, the signal that is returned by the population is decreased, okay? That kind of loss of coherence is referred to as roughly as sort of the T2 decay, all right, the time constant that it takes for these things to kind of get out of alignment with one another. Okay, that's all we really need to know at this point about T1 and T2. But here's where things get interesting and relevant to the sorts of bold fMRI type experiments we do. So it turns out that functional MRI is mostly performed using something called bold, or blood oxygen level dependent MRI contrast. Okay, so what is this stuff? Where does it come from? Well, it turns out that in one of a number of fortuitous properties that Mother Nature has provided us, hemoglobin, which is the primary oxygen-carrying molecule in the blood, has different magnetic properties depending upon whether it's bound or unbound to oxygen. Okay? So I always forget this. It's the deoxyhemoglobin is the more magnetic one. Someone back me up on this one. Is that right? That's right. Diamagnetic is the, or paramagnetic is the oxyhemoglobin, is the deoxyhemoglobin, right? Right? Yes. Okay, good. So hemoglobin, which you guys remember is the primary oxygen-carrying molecule, right, has at its core, it's basically a whole bunch of protein with an iron molecule, or the iron atom right in the center, okay? And depending upon whether or not O2 is bound to hemoglobin or not, that iron atom has slightly different magnetic properties. It's such that when there's no oxygen there, it's ever so slightly magnetic, okay? It has ever so slightly magnetic field properties. But when the oxygen is bound, it doesn't have any sort of magnetic properties whatsoever, okay? So what does that mean? Well, we talked about how the T2 signal represents the decay or the loss of coordination between these different protons, okay? Well, we know that these protons, when we start off in this notional example, are all spinning at the same frequency. And we also established that one thing that affects the speed with which these protons spin is the magnetic field that they see. Okay? The stronger, I think this is the case, the stronger the magnetic field they see, the faster they spin. The smaller the magnetic field they see, the slower they spin. Okay? Well, what if it was the case that we placed, in this little example, a little bar magnet down here? Right? We just had a little extra magnetic field here, so that the magnetic field was not smooth across this entire representation of, say, this is a voxel, which contains a bunch of water molecules or protons. Suppose down here the magnetic field was a little bit stronger than we saw up here. Well, what would happen? Well, these protons here, which are a little bit closer to this stronger component of the magnetic field, would spin just a little bit faster than these protons over here that are seeing a slightly weaker magnetic field. Well, if these ones are spinning just slightly faster, then they're going to tend to get out of phase or alignment with the ones which are spinning slightly slower. Okay? So if there is what's called inhomogeneity, I'm not going to write that down. If there is inhomogeneity in the local magnetic field, okay, one property or one effect that's going to have is that protons which are in one stronger little part of the magnetic field are going to spin faster than protons which are in a weaker part of the magnetic field. So as a consequence, this T2 decay is going to be more rapid in the face of an inhomogeneous magnetic field, okay? Because the protons will be tending to spin at different speeds, and so more rapidly will that signal decay. Well, now we've established that hemoglobin, in its deoxy state, is going to act as a little bit of a bar magnetic field. So what if we had sort of a bunch of red blood cells here with deoxyhemoglobin in them? Okay, well these, all the iron atoms, which are contained within these hemoglobin molecules, which are contained within the red blood cells, are going to tend to then disrupt the magnetic field, which is right nearby it. Okay, and thus, if you had a tube of blood which was deoxygenated, right, had deoxyhemoglobin, this T2 decay would be more rapid than if you had oxyhemoglobin about. Okay. Well, it turns out this relationship, or this effect of hemoglobin in its oxygenated or deoxygenated state, is the basis then of how bold fMRI works. Okay? In effect then, what we're measuring when we create one of these bold fMRI images of the brain is we're measuring something called susceptibility, which is a measure basically of this inhomogeneity of the magnetic field. Okay, which is induced by a lot of things, but fortuitously one of the things which induces this is the relative concentration of deoxyhemoglobin. Okay? Now it turns out, of course, that lots of other things can introduce susceptibility. If you have someone who comes into the scanner wearing like a metal barrette on the back of their head, then that will also introduce sort of we'll put metal next to there and sort of introduce this sort of susceptibility effect. Lots of other sort of much more common things. So just the air tissue interface at the sinuses or in the ear canals also introduces susceptibility because that air tissue interface tends to concentrate magnetic field lines. You'd have to ask a physicist why that happens. I couldn't tell you. But that tends to produce susceptibility effects there as well. Okay? And this is why in bold fMRI signals we tend to get rather poor appearing images from right down near the sinuses and near the ear canals, because those are locations where the susceptibility effect is quite strong and that T2 signal just gets blown away. Okay? All right, so now all this would be for naught if, so what would we have so far? Well, we would have a technique which would be pretty good for measuring kind of the oxygenated or deoxygenated state of the brain, which, might be interesting if you're studying physiology and you want people holding their breath and stuff like that. But, we want to take this a step farther. We're actually interested in neuronal activity, and it turns out that there's yet another incredibly fortuitous property of the organization of the brain and its physiology, in that there is a local linkage between neuronal activity and vascular response or blood flow, okay, such that if an area of the brain increases its level of neuronal activity, there is a commensurate increase in the blood flow that occurs to that one area of the brain. Okay? And so as a consequence then, that brings in fresh blood, which is more, it turns out that at least under normal physiologic conditions in adult human subjects, you get a greater blood flow response than you have oxygen demand as a consequence of that neuronal activity. So as the effect of all that is you bring in more oxygenated hemoglobin than is necessary. And that leads through the series of physics and physiologic steps to then a decrease in the bold fMRI signal at that location. Or, I'm sorry, an increase in the bold fMRI signal at that location from bringing in more oxygenated hemoglobin, thus flushing out the deoxygenated hemoglobin, which is causing the susceptibility effect. Okay? So to kind of sum all that up, if you have an increase in neuronal activity, that leads to an increase in the local vasculature. And actually, the precise details of this are still very much under study, and there's an awful lot of elements to it that I'm just skipping over. But in any event, that increases your oxygenated hemoglobin, which then decreases susceptibility effects, which increases your bold fMRI signal. Okay? So you can think of then each image that we get of the brain over time then as being, in essence, a reflection of the concentration of deoxyhemoglobin at each point in the brain during that time point when you acquired it. And then in turn, you can think of that concentration of deoxyhemoglobin as reflecting the level of neuronal activity that was present there at that point in time. Okay?
Is the bold signal just the inverse of the susceptibility effect? Is that something else?
Yeah, more or less. Yeah. Right, and again, so I'm running roughshod over a lot. I didn't talk about T2 star. There's sort of the relationship between T2 and T2 star, and it refers to the components of the magnetic field inhomogeneities that you can correct versus those you can't. And so we're not even going to kind of get into any of those details, which starts to stretch the limits of my understanding of a lot of the physics of it. But at least this, I think, will carry you in good stead for understanding the sequence of events that goes from neuronal activity to bold fMRI signal. Okay? So, Now, it turns out that, as I mentioned, a lot of these elements that kind of go along the way are subject of a fair bit of intensive experimentation, and people are very interested, for example, in what this connection is. How does neuronal activity relate to local vasculature changes? And so let me just say one word about that, and that is that for a long time, the assumption always was that it was the spike rate. So neurons have a rate with which they can fire, and it was just presumed that the speed of that firing is related to the caliber change in local vasculature that occurs. As time has gone on and people have looked into this a little bit more, it seems to be the case that that's not going to be strictly true, but instead the local vasculature change seems to be related to the local field potential, which is, you can think of it almost as kind of the population synchronous firing of a population of neurons. So it's kind of the dendritic or synaptic local field potential that seems to be driving this primarily. It turns out, under a lot of circumstances, local field potential and spike rate are fairly correlated, but you can certainly find cases where they're not correlated. One example of that is in drowsiness, where you can show, and there was some very nice work presented at Human Brain Mapping just this past spring, that in cat cortex, you can show that even when the cat's becoming drowsy, as measured by EEG, showing attenuation of the alpha and all the rest, that the spike rate of firing continues when you present visual stimuli, but the local field potential starts to be lost. That is, the synchronous firing starts to be lost, even though individual neurons are still firing. So you can imagine that there are circumstances where these two things will start to become dissociated. But luckily, as a first-order approximation, spike rate tends to be pretty well related to local field potential, and it's the local field potential that seems to be driving the bold fMRI signal for the most part. Yeah?
Could you explain susceptibility again? I don't understand how reduce susceptibility to increase bold fMRI signal.
Okay. So the basic idea is that susceptibility is kind of the static field in homogeneity. It's kind of the places where the magnetic field is not even. So we have this very large scanner. It aims to produce a very even magnetic field across the bore. And places where there is either an air tissue interface, which concentrates magnetic field lines, or a collection of deoxyhemoglobin, will tend to perturb or alter the otherwise smooth topology of the magnetic field. And so that effect, as we talked about, is to increase the T2 rate of decay, because the protons will be spinning at different rates as a consequence of some seeing a stronger magnetic field than others. And so bold fMRI is weighted towards measuring this, in effect, this T2 type of decay. So that the more inhomogeneity that's present in the field, the more rapidly the signal decreases, so the lower the signal value is, in effect, that you're measuring. Okay? That's probably about the best I'm going to be able to do of trying to put this together. Okay, so we can describe an awful lot of the elements of this system that relates one thing to the other. Okay, and it would be kind of a pain in the butt if any time we wanted to do a bold fMRI experiment, we had to sort of explicitly understand each of these stages and each of these relationships. If we had to know kind of how changes in local vasculature give rise to changes in the concentration of oxygen and hemoglobin, if we had to really understand, as opposed to the sort of thumbnail sketch I gave you of how these two things are related. But it turns out that luckily, if you just slept through the first 20 minutes of this presentation, or you just arrived late, it's okay, because we can actually ignore an awful lot of these details that go into the transformation of neural activity into bold fMRI signal. Why is that? Well, because we can characterize, instead of each of these individual steps that leads to this transformation, just this big step here, how neural activity relates to bold fMRI signal. Okay? And so here's where our conversation is going to turn to a discussion of systems. I'm just realized I'm jumping out of order from what I put down in the outline, but I'm sure you guys are going to forgive me because I'm on a roll. All right, so what we're going to get into right now is a talk about systems. So what's a system? Well, when an engineer is trying to understand a thing that is presented to her, she characterizes it sometimes in terms of a system, which is a notional thing that takes input and provides output. Okay? And you can think of the world is full of systems if you want to look around for it. All right? A car is a system where the input is the pressure that you put on the gas pedal, and the output is the speed with which the car moves, right, or its velocity. And lots of other, toaster oven is a system where the buttons that you press are the input, and then the heat that comes out within the chamber is the output, and so on and so forth. Well, you can think then of bold fMRI as being sort of a system too, where the input is the neural activity, characterized either as local field potential or spike rate, but we'll just talk about spike rate for now. And the output is the bold fMRI signal that is obtained. Okay? Input, output. Fair enough. Well, So that doesn't really get us too much farther, except it turns out that there are certain sorts of systems which are rather amenable to study. Okay? Some systems are fairly complicated, and you'd have a very hard time understanding what it is that's transforming the input to the output, or more specifically, being able to predict, given some input, what the output will be. Well, there is a particular type of system which is very lawful in its transformation of input into output, and thus is very good at being able to let you predict what the output is to any arbitrary input. And that sort of system is what's called a linear system. Okay, so what's a linear system? Well, so a linear system has some properties, which I think I jotted down here in the outline. And those are superposition, homogeneity, and invariance. Oh, Lord. So what are those things? We won't go into excruciating detail, but let me just give you a sense of what some of the properties of a linear system are, and of systems in general, through the use of a quick analogy. Okay. So I really have been giving this lecture for too long, because I'm at the point now where the standard analogies that I use are getting so hackneyed and cliched. I've used them like every year that I'm embarrassed that I've tried out the same damn analogy like every year for those people who are foolish enough to have come back year after year after year. What's that? No, donuts and faces will be coming up. But actually, this is the toilet analogy. We start with the toilet analogy before we move to donuts and faces. Yes, another example of a system that takes input and provides output, right, is a toilet. So you might ask, sort of, what is the input and what's the output to the toilet? The input, of course, is the flushing of the handle, right, and the output is the water that's leaving the system. I sincerely hope all of you are considering the same inputs and outputs for the toilet system. So you can imagine, then, that your job is to try and determine what the input to the toilet system has been by measuring the output, the water flow that's come out of it. So why on earth would you want to do something like that? Well, times are tough. Maybe you're a graduate student, and you've decided to do a study on the toilet usage as a consequence of the Super Bowl halftime show. And so your method of collection of data is going to be to wait in the water outflow systems that lie underneath the street. And you're going to measure the amount of water that's coming out from each house over a period of time. And you want to try and determine, how many people are in each house or how much the toilet gets used as a consequence of, the Super Bowl halftime show. Okay, so the system then is, the output again is water flow out, and the input is the flushing of the handle. So one thing we can say is that the inputs and the outputs have different sorts of time scales. So if you pull the handle, that's just sort of a unitary, momentary event like that. So suppose this is a graph of handle movements. Handle movements. And so most of the time the handle is quiescent, but here comes Britney Spears on the screen to sing, and so everybody rushes upstairs. And one sort of movement of the handle in an otherwise sort of quiescent period of time, right? Well, if you're down in the sewer system measuring the water that flows on out from this thing, what you'd see is that after the handle flush, there's a brief delay, because it takes a little time for all that water to move on down through the system. But then there's going to be a rise in the water, and then it's going to slowly decay and come back down to baseline like that. Okay? So you've now characterized kind of what it looks like for one movement of the handle to produce that kind of pattern of water outflow. Okay? So if you're down hanging around in the sewer system, and you measure this, you'd be able to say with probably some fair confidence that the events that occurred up in the house where there was a handle movement there was a handle movement there, and there was a handle movement there. Okay? So you're able to work backwards by knowing kind of what the response of the system was to one flush. You can say, oh, okay, here are some more flushes. So I can work backwards and know that there were handle movements that occurred at those periods of time. Okay? Now, what if you obtained something like this? Now, at this point, we're going to have to posit the existence of not your normal toilet, which has a rather long refractory period. You flush that handle, and then you have to wait and wait and wait and wait until you can sort of flush it again to get to go again. But let's imagine that this street is equipped with toilets which have the very nice property that they're kind of like the super strength industrial toilets we have around here, right? Where it doesn't matter, you can kind of go there and give that handle another jiggle right away if you care to. So imagine that you are standing down there, you see this, and then some period of time passes, and you see this. Okay? Well, you would probably be able to infer that what happened was there was one flush here, and then there were two flushes here, which kind of occurred close enough together in time that the water outflow from the first one overlapped with the water outflow of the second one. Everybody with me so far? Right? Everyone's able to kind of make the handle level inference on the basis of the water outflow, right? Okay, and let's further imagine that this toilet is not just sort of has this great property of you're able to kind of flush it as often as you want, but you can also kind of grade your flushing, right? So, you know, sometimes you just might want to give it a little bit of a flush, but sometimes you want to give it sort of a super power, extra pull down on the handle, hard flush, right? So imagine that there's two sorts of flushes that you can provide. So if this would be a regular flush, here's a big flush, and it has the consequence of just producing twice as much water output, okay? So if I double the size of the flush, okay, I create twice as much water output. Now, of course, because of some of the properties of the system and the way that the water, you know, travels and everything else, it's the case that, you know, it would be very hard actually for you to distinguish between two flushes, or one very hard flush like that, and two flushes which occurred almost identical in time to one another, okay? In the way that I've described the system so far, these two things would produce pretty much identical output, okay? Because what you have here is one double-sized flush, and what you have here are two normal-sized flushes, which are just summed up to give you one big double-sized flush, okay? So that it may come as no surprise to all of you that the system I've been describing is a linear toilet system, okay? So a linear toilet system has a number of properties. Okay, one is superposition. That is, if I have one flush and then another flush that comes after it, these two flushes are going to kind of add together to create a composite flush. Okay? It also has scaling properties such that if I double the size of the flush, an extra hard movement on the handle, it creates twice as high of a flush. Okay? And I've already forgotten what the third property is. Invariance, right. It gives you the same darn flush every time you move the handle, okay? It doesn't matter if you flush the toilet at 3 a.m. on a Wednesday or at 2 p.m. on a Tuesday. It always gets the same water outflow for the same movement of the handle, okay? So these are properties of a linear system. So if the toilet system has these properties, then it's the case that you can always work backwards from the water that flows out into the sewer system to figure out what the input was to the system in terms of handle flushes, okay? And it may come as further no surprise to know that this toilet system analogy is one that stands in quite readily for the bold fMRI response. So let's actually clean up our discussion and move back to bold fMRI. And know then that we can characterize in the exact same way neuronal activity and the blood flow response that ensues, or the bold fMRI signal, right? So if this is neural activity up here, and this is a bold fMRI signal, okay, we can characterize that if there was sort of, suppose you have your electrode in primary visual cortex, okay, and you are recording neuronal activity from that area from a college student who has foolishly volunteered for your experiment, and they're sitting in a dark room, and at a sudden moment you flash lights, right? And so what you would have is a neuron that was quiet, then the lights come on, and then it's quiet again after you turn the lights off again, okay? So what that would result in from the bold fMRI signal is a rise in blood flow that follows this flash of light and the neuronal activity that ensues. The blood flow rises, peaks, comes down, actually goes back below baseline for a moment, and then returns to the baseline, okay? This is what's referred to as the hemodynamic response function, okay? Hemodynamic response function, because it is a blood flow or hemodynamically driven effect, and it's the response function for a brief period of neuronal activity. Okay? Is everybody with me so far? So in very much the same way that flushing the toilet produced a characteristic water flow pattern, right, in the sewer system, having a brief, intense period of neuronal activity produces a characteristic change in bold fMRI signal as a consequence of this characteristic change in blood flow for a particular point in the brain. Okay, people look like they might have questions. No questions? Everyone's perfectly cool with that? Yeah, Dan?
Does cellular density affect the neuronal environment, or is that sort of a
Okay, so the question is, so what affects the neuronal firing rate? Cellular density, all the rest. There's a lot of things that can affect their neuronal firing rate, tons and tons of things. So let me pause for a moment to introduce the two systems concept, okay, since you have raised the question. So what's the two systems concept? Well, the idea is that we have neural activity here, and we know neural activity is related in some way to bold fMRI signal. Okay? Now, we've spent most of our time so far discussing the properties of this system, neuronal activity input, bold fMRI signal output. It turns out that but for a vanishingly small proportion of the audience here, this system is of no interest except to just try and get it over and done with and understood. The main thing that you're interested in is this mapping over here. Cognition and consciousness and, stimuli and instructions and all that sort of stuff and how that relates to neuronal activity. Okay? That's really what probably most of us are interested in. When I present sounds in the left ear, what kind of neuronal activity do I get? When I, have someone try and do working memory and hold on to information, what kind of neuronal activity I get? But I don't get to look directly at neuronal activity, right? The agonizing aspect of all this is that I only get to look at these bold fMRI signals, which are, sort of blood flow and big chunky parts of the brain and all the rest. And I have to work backwards from this rather crude measure to get back to the neuronal activity. Okay? So this is the base of this sort of two systems description. And that is that we measure bold fMRI signal, okay? And knowing that this relationship is a linear relationship, we can work backwards and say, okay, given the bold fMRI signal that I observed, here's what the neuronal activity likely was that produced it. Okay? Now knowing that, now I can start to draw inferences on this level. Okay? What was the relationship between, sounds that I presented and the neuronal activity that I measured? Okay? So the reason I introduce this now is because it's a pretty good thing to keep in mind that there are these two systems and that they have fundamentally different properties. Okay? The system that transforms neuronal activity into bold fMRI is mostly linear. We'll talk about that in just a moment. All right? The system that converts cognition into neuronal activity is manifestly not linear. Okay? It is probably the farthest thing from a linear system you can possibly find. All right? So even just something as simple as in primary visual cortex, if you present flashes of light, the transformation of flashes of light into neuronal activity is not linear. Right? You actually get this sort of effect where if you put a flash of light, you'll get an initial sharp increase in neuronal activity that then sort of decays like this. But if you put two flashes of light together, you don't get sort of this plus this. You get the same sort of spike and then just sort of a longer decay or whatever. I mean, you get these sort of very complicated relationships between sort of stimuli and input and the sorts of neuronal activity that you get. Okay? Now, we would be completely hosed if this was a completely nonlinear system and this was a completely nonlinear system. Because we'd present stimuli and we'd measure some kind of signal and we'd have no idea how to relate the two of them. Okay? But thankfully, the relationship between a neuronal activity and bold fMRI signal is quite lawful, right? Quite lawful in the way that we've already started to describe, that it has these properties of being a linear system. So as a consequence, then, we can do this working backwards and then relate neuronal activity to this. So Dan's question was a very good one. So what is it that affects neuronal firing? Is it could it be the density of neurons that are in a location? How about this local field potential thing? What happens? And I'd say those are all very good questions, and they're all System 1 questions. Okay? So System 1 questions are the sorts of questions that most of us, once we leave this room and this godforsaken 8 hours we're going to spend together, those are the questions we're going to go answer. Okay? But by and large, while we're here in this room, we're mostly going to be addressing ourselves to System 2 questions. Right? Because we just want to get this business out of the way of relating bold fMRI signal to neuronal activity. Okay? All right. The two systems model. We're going to go for 5 more minutes, and then you need to do a little tape switch-o, right? Okay. So 5 more minutes. So let's finish up we were just getting into the nitty-gritty of a linear system and of linear systems modeling of bold fMRI data. All right, so I detected, yes?
It must be important, I think. I just have trouble mapping on the superposition homogeneity and invariance to those 3 principles you showed. Superposition was fine. It was when you have 2 overlapping
Right.
signals. Then invariance was?
Invariance is that you get the same flush, you get the same water flow every time you move the handle.
Okay, so there's no.
So it isn't modulated over time, for example. Homogeneity.
It says homogeneity here.
Homogeneity. Oh God, what's homogeneity? Yeah, I think it's a scale. I think scale. It's basically a scaling effect. Such that twice the input gives you twice the output. Okay. So if you give a twice as hard handle flush, you get a twice as big.
Does that violate invariability?
Yeah.
Great.
No. So for the same input, you always get the same output. That's invariability. Same input. Oh yeah, because otherwise, if you had a system which always provided the same output no matter what the input was, then that would be a system which would be quite easy to understand. It would have just the same output no matter what. Yeah. No. So this is so I should clarify. Invariance means it's the same output for the same input. Okay. All right. So a linear system has several remarkable properties, or very useful properties, and one of the best is this thing called the impulse response function. The impulse response function, you might notice some similarity to the hemodynamic response function we just talked about a moment ago, is a measure or a characteristic of the system that defines the transformation of input into output. So it turns out, and so this is a remarkable thing about linear systems, it turns out that no matter what the input is that you provide to a linear system, you are able to make a precise estimate of what the output of that system will be, as long as you have knowledge of the input and this thing called the impulse response function. Okay? This is quite a remarkable thing. And this is the basis of our ability to be able to predict, when we do our bold fMRI experiments, what the bold fMRI signal will be based upon the stimuli we presented and the neuronal activity that we expect to produce. Okay? So let's walk through this real quick, because this is an important concept. So the idea is that the impulse response function is the response of a linear system to an impulse input. So what's an impulse? An impulse is technically an infinitely brief, infinitely intense input, a spike, right? So in the example of our toilet example, it would just be like a super hard, like, crank down on the handle for an infinitely brief period of time. In the example of the bold fMRI system, it would be a very brief, very highly intense period of neuronal activity at one point in the brain. Okay? So the response of the system, and I've already previewed for you what the impulse response function looks like for the bold fMRI signal. It is this thing, the hemodynamic response function, a rise and decay of the bold fMRI signal in the time that follows this brief period of neuronal activity. Okay? And this thing has some characteristics we can talk about. Its peak comes between about 4 to 6 seconds. There's typically an undershoot, which arrives at about 10 seconds. And the whole darn thing is over somewhere between about 12 to 16 seconds. Okay? So what are some things that we can observe immediately about the hemodynamic response function, or this impulse response function for the bold fMRI system? So the first thing is that it's delayed, right? You have this period of neuronal activity, and it takes about 4 seconds to kind of get the maximal response to the system from that very brief, very rapid period of neuronal activity. The second thing is it's dispersed. That is, you had this very sharp, brief period of neuronal activity, but this gives rise to this thing which is so languid and just spread out over time, over 12 to 16 seconds. Okay? So delayed and dispersed, right, response to this. Well, if bold fMRI is a linear system, and we can characterize this thing called the hemodynamic response function or impulse response function, then we should be able to predict what the output of the bold fMRI signal will be to any arbitrary pattern of neuronal input. And we've already had some practice with that when we were talking about a little bit with the toilet example, right? Where we started to superimpose flushes and put them one on top of the other. But let's just follow through with this exercise. So imagine that you had an experiment where you wanted to present a period of neuronal activity. So you had some light flashes. You had a flash of light here, and then another flash of light 6 seconds later. So that's about 6 seconds between the two. And then another flash of light, which was 12 seconds. We'll make that 18 seconds apart, say. So 6, 6, 18, and then let's say you had 2 here, which were right on top of the other. So another 18 seconds later, you have 2 spots which are right on top of one another. Okay? So we're in a position to predict kind of what the bold fMRI signal will look like as a consequence. And one way we can do this, actually, is by taking the hemodynamic response function to each individual event and then summing them up. Okay? And this is where the linear part of a linear system comes together, because it follows sort of this linear systems or linear algebra approach. So if this is the response, so let's map out here the bold fMRI response to this first flash of light. If this flash of light were to occur in isolation, or this period of neuronal activity in isolation, we'd get something that looks like this. Okay? And this one would produce something that looks like this. And this one would produce something that looks like this. And then this one would produce something that looks like this. And the last one would be nearly overlapping with that first one, like that. Okay? So imagine then we have the thought experiment of what would the bold hemodynamic response look like to each of these little spikes of neuronal activity in isolation. Okay? So if we now want to figure out what the bold hemodynamic response function would look like to these spikes all kind of added together, if you actually presented them all in the same time, kind of as I've laid out in this timeline, all you got to do is just add each of these lines together. And that gives you the summed response, which I'll draw, just breaking convention for a moment, above this response. It would look something like this. Right? So that would be, in effect, summing up these things to kind of produce that curve up there. All right? So this is a remarkably powerful ability, right? So we can take any arbitrary pattern of neuronal activity input, and if we have some knowledge of what the response to any one spike is, we can describe what the response would be to any pattern or arrangement of spikes that we could possibly conceive. Well, that's a tremendously powerful thing, and this is actually ends up being the basis of the approach that we're going to use. Okay, so it's 10 o'clock. You guys have been sitting in your chairs long enough. Let's grab a quick, glass of water, go visit the toilet system, and we'll be back here in your seats maybe, let's give it 5-7 minutes, and we'll start up with part 2.